Seen or heard before that visible light can be thought of as both a particle and a wave. Now we know that particles, the photon here, carry momentum and energy. So it's not too big a stretch to imagine that all electromagnetic radiation can be both particle or wave, and thus carry their own momentum and energy. So in this lecture we want to look at the energy flux due to an electromagnetic wave anywhere in space, but we also want to look at the momentum flux, which is probably better known as radiation pressure. Now radiation pressure has some very cool effects, which we will look at in the last video of this lecture about solar sails and traveling between planets using solar-powered spaceships. Okay, but before we can get to energy flux, we first need to do a quick revision on energy density. So we need to know the energy density from both the electric and magnetic fields of electromagnetic wave. So we can do this by separating the energy density into the electric part and the magnetic part. And we'll do this by looking at a parallel plate capacitor and the energy stored in that, and a solenoid to have a look at the magnetic energy density. So to begin with, we're going to have a look at the parallel plate capacitor. So the energy created by the EM field inside the plate, the capacitor here, so the plates are at a distance d and they have an area A on the side. So we found out before that the equation for the energy stored, the energy between these two plates is equivalent to this. Now here is the electric field strengths. This is the volume of the parallel plates. And so if we wanted to get the energy density from this, it would simply be a matter of dividing it by the volume, which is AD. So what we end up with is that the energy density in joules per meter cubed is just equal to this. From this equation you can see that the electric energy stored per unit volume, which is the energy density, in any region of space is proportional to the square of the electric field strength. Now this is true even without a parallel plate capacitor, so it is true anywhere in space. Just as the energy stored in a capacitor can be considered to be the electric field between the plates, so can the energy in an inductor be considered to be stored in the magnetic field. Now here we have a solenoid, which you've seen before. It has n turns, it is L long this way, and it has an area on the side equal to pi r squared. So the energy from this solenoid here, we've seen previously that it's equal to this, where AL is the volume that the entire solenoid takes up, and B is the magnetic field strength. So we can do exactly what we did before and rewrite this as the energy density by dividing it by the volume of the solenoid. This is because we can think of the energy as residing in that volume enclosed by these n windings of the solenoid. So the volume is then equal to AL. So the energy density, here we'll subscript with a small b, becomes okay. Again, even though this is derived for the special case of a solenoid, it is actually valid for any place in space, which is good. Yeah. So what we really want is the total energy density of an electromagnetic field anywhere in space. Now this would be equal to the energy density of the electric plus the energy density of the magnetic fields. Now if we just add the two equations we've just worked out together, we obtain the total energy density due to an electromagnetic wave anywhere in space. So here, just a reminder that E and B equal the electric and magnetic field strengths. of our electromagnetic wave, but we can actually write this in terms of just the electric field. Now we would have learnt in the relation that the magnetic field strength is equal to the electric field strength divided by c, the speed of light. Now, we also know that the speed of light can be rewritten as equal to this. Now, if we substitute both of these equations into the above formula here, we can get the total energy density due to an electromagnetic wave purely in units of the electric strength, the electric field strength. Alright, so that's pretty cool. You can actually see from this equation that the magnetic field strength is, that the energy density associated with the magnetic field is equal to that of the electric field. Now, we can actually make this entire equation in terms of just the magnetic field, for fun. So to do that, we use exactly the same equation as above, and we can obtain this version of the equation. And again, you can see that the energy density due to the magnetic field is equivalent to that of the electric field. So to do this again, we can actually change this equation into involving both E and B again, but in a different way. So from using the equations above, what we can do is we can do this. So in the end, we have three versions of this equation. This one here, which is the energy density of the electromagnetic field only in terms of the electric field strength. This one here, which is the energy density in terms of only the magnetic field strength. And here we have the energy density in terms of both the electric and magnetic field strengths. And all three of these equations are valid in any region of space at any instant.